Hello and welcome to the Data Engineering Podcast, the show about modern data management. When you're ready to build your next pipeline and want to test out the projects you hear about on the show, you'll need somewhere to deploy it, so check out our friends over at Linode. With their managed Kubernetes platform, it's now even easier to deploy and scale your workflows, or try out the latest Helm charts from tools like Pulsar, Pachyderm, and Dagster. With simple pricing, fast networking, object storage, and worldwide data centers, you've got everything you need to run a bulletproof data platform. Go to dataengineeringpodcast.com/Linode today, that's Linode, and get a $100 credit to try out a Kubernetes cluster of your own. And don't forget to thank them for their continued support of this show. Your host is Tobias Macey, and today I'm interviewing Yaron Haviv about Iguazio, a platform for end-to-end automation of machine learning applications using MLOps principles. So Yaron, can you start by introducing yourself?
Hi everyone, I'm Yaron. I'm CTO and co-founder for Iguazio. Many years in high tech, been in companies like MLOps and others. A lot of experience also in data analytics and data engineering, which is a good segue to this podcast.
And do you remember how you first got involved in the area of data science and analytics?
When I was in MLOps, I was heading all the data center activities, open source projects, Hadoop, Linux, working with databases. We helped build things like Oracle Exadata and SAP HANA and other solutions. MLOps is sort of an infrastructure player, and right now it's part of NVIDIA. My role was essentially to help optimize the performance of each one of those databases, the storage layers, etc. So at a certain point, we said, maybe we can do it better. And we formed a company. We brought some key architects from other companies like IBM and EMC and others. And essentially, our initiative was to build something area of a multi-model database, essentially something that performs really, really fast, but also can do analytics and sort of historical data and real-time data and all of that. And obviously, the key application for that is data science. People that need to do training on one end, but then inferencing on the other end. And one of the biggest challenges in data science is around data, and we'll probably get to talk about it.
Can you give a bit more background about what it is that you've built at Iguazio and some of the story behind how it got started and your motivation for creating the company?
Essentially, what we started with is sort of an extremely high performance database for those kind of applications of machine learning and analytics. We started with was essentially using traditional flash storage for getting the performance of in-memory databases, which we still do, sub-millisecond latencies and things like that. So using that, you can essentially consolidate a lot of the different layers. You don't need to move things around. You just point to them with different references. And we just started exposing different APIs into that engine so people can work against it with Spark, with Pandas, with SQL, with NoSQL, with Presto, all the traditional tools. So then it helped build machine learning pipelines. So as things progressed, we needed a lot more flexibility for the computation part. So we started forming serverless engines that are very flexible but very high performance. You've probably heard the term serverless functions like Amazon Lambda, etc. But those are really slow and they're stateless. So what we've created is some engines. One of them is called Nucleo, very popular, about 4,000 stars in GitHub, which is about 100 times faster than Amazon Lambda, and it's also stateful. So you can actually build transformations, real-time transformations for data. You could build like inferencing for a model. You could take data from any type of source, whether it's HTTP, JSON packets or Kafka streams and all that. It has native integration with Kafka and all of that. And then the next layer that we built on top of it as we progressed was actually all the machine learning pipeline that goes along with it, like the serving layers, the model monitoring, the training, the ingestion and preparation of data before the training. And so essentially we created a stack which its key role is operationalizing the machine learning side. So most of the platforms in the data science side are really more about, okay, let's do some experiment and training, and maybe we throw some models into like an endpoint around HTTP. But all of our customers, essentially what they had to build is a real pipeline, which involves transformation of lots of data at scale, and then doing training and maybe retraining. And then you also need to be able to build exactly the same data on the production serving pipeline attached to operational databases and all of that. So this is our focus, is building operational pipelines. And we can talk later about some of the users and examples that we have.
One of the interesting things about machine learning and data science is that there are drastic differences in terms of the scale at which they might be executed. So, a hobbyist data scientist might pull down a static data set that has the training data already labeled, and then they will, build some sort of experiment to try and do some inference on it, like the New York taxi cab data set that's been used in a lot of examples, or MNIST.
Yeah, we also have that in one of our demos.
Exactly.
Yeah.
And then on the other side, you might have a large scale machine learning operation where you're pulling in real time clickstream data from a massive web property. So you're looking at, thousands or millions of events on a daily basis. So that's a very different order of scale and magnitude and requirements for the pipelines.
So this is exactly the challenge that we're addressing. Okay, that's the problem. A data scientist opens up a Jupyter notebook. He gets some CSV file that someone extracted for him from some data engineer or whatever, and maybe a few CSV files, like one from every database or table, and he starts playing around with it in his Jupyter. As it gets slightly larger, his Jupyter is getting out of memory, if you know the phenomena. But now that assuming he needs to do exactly the same stuff at scale, what are his options? Now he needs to move from pandas, very nice Python semantics, to SQL and code against data warehouse with like where and join and all that stuff. Or maybe he needs to start learning Scala or the variations of Spark with Python and things like that in order to build some. It's not their role. They don't understand any of that because they're looking for something which is more Pythonic and more sort of abstract. There's also a lot of transformations that built for machine learning are not really popular on sort of the databases side, like feature imputing, scaling of features, encoding, and things like that, but still requires a lot of processing across lots of data. So this is really where we built our open source frameworks around our database to be able to make it very transparent to the user as if he's working on Pandas or Spark or whatever, but be able to process 10 or more times the amount of data. And actually, instead of storing it in memory, we store it in Flash, which is relatively cheap, process that data. And we created abstraction layer on top of it so we can really program this logic once, and then you can use exactly the same abstract logic for the training, for like batch preparation, and for serving, for like real-time serving, leveraging the low latency access. And this really eliminates a lot of those problems that you just spoke about.
Yeah, that's definitely interesting because, as you said, if you go from a handful of CSV files to real-time data streams, there's a massive learning gap in terms of the familiarity that any engineer or data scientist might have, or the capacity that the organization might have for being able to deploy and support those types of technical requirements. If you can just talk a bit more about some of the ways that those challenges manifest as you go from theorizing about a problem, experimenting with a sampling of data to see, can you get anything interesting out of this, to then trying to bring it into production, and some of the impedance mismatches that occur in that journey.
One of the things that we've worked a lot on the last year is something called the feature store. I don't know if you've heard the term. In Google, Uber, Netflix, and so on, the way that they're doing it is every data engineers or even data scientists to produce features. What is feature? Is essentially processing a bunch of data elements and creating something meaningful. Think like you have a stream of data of like ticks or monetary transaction. What you really care about on the machine learning side is like what's the average transaction volume, or how many products a customer typically buy in a day. That's a feature. And each one of those features, if you think data engineering wise, essentially can translate to like a SQL query and all of that, and you can build that. Some features are more complicated, like time-oriented aggregations. SQL is not the native language for those kind of things. So in a feature store, you define the business logic to create the features. You place those features in a catalog. And then when the data scientist wants to train a model, it essentially says, you know what, I need the average age for users. Everything has sort of a name, it's labeled. And behind it, it's hiding all the data transformation logic, all the analytics logic behind that feature. So it goes and feeds that into the training, it runs the training, and then as you go into the operational aspect, this is where the real fun begins. Before what we said is like it goes to a data warehouse, runs some SQL query, gets the features, and does training. But when you go into production pipeline, it looks pretty different. It's like weblogs, it's HTTP APIs, it's like accessing an external service to grab the data because you need the data right now, like listening on a clickstream. It probably arrive using Kafka, but as you get the clickstream and there's like a user ID, you may want to know some data about the user, like a gender, and like when was it first registered or whatever. That means that you need to now go to a NoSQL database and join, essentially go fetch the record of the user and combine it to it and so on. That making extremely, exponentially harder than just doing some queries on a data warehouse. And really where the industry trend today is to build those abstract logics built into something called a feature store, where you just define what are the sets of transformation. And there's machines, essentially software programs that translate that into two parallel universes, one for more batch kind of pipeline, and the other one is for real-time pipeline. This is really where we leverage the serverless technologies that we built, that essentially this abstract logic compiles into a serverless function. And that serverless function is running in real time. Like take an example of processing a Kafka stream. Nucleo has auto-scaling features and integration with Kafka and rolling upgrades and lots of other capabilities where you just need to focus on the business logic. So the feature store compiler, if you will, builds the pipeline into the serverless function, deploys the serverless function, and then the serverless function has a life of its own. It just listens on Kafka. It will scale to fit the exact workload. It will write the results into our NoSQL or into like Parquet files for offline use or for other forms like to another stream to inference on or whatever is needed. So that level of abstraction is making the operations of machine learning significantly simpler because then you essentially define those features, you put them in a catalog, someone just collects them into his application, and collecting them is not like a catalog data engineering. It's not like just selecting sort of a data set. Essentially, the features hide behind them the entire data engineering pipeline. It's also a lot of computation when you say feature. It looks abstract, but it's the entire like stream processing or data analytics logic is hidden behind those objects.
RudderStack's smart customer data pipeline is warehouse first. It builds your customer data warehouse and your identity graph on your data warehouse with support for Snowflake, Google BigQuery, Amazon Redshift, and more. Their SDKs and plugins make event streaming easy, and their integrations with cloud applications like Salesforce and Zendesk help you go beyond event streaming. With RudderStack, you can use all of your customer data to answer more difficult questions and send those insights to your whole customer data stack. Sign up for free at dataengineeringpodcast.com/rudder today. In terms of actually digging more into how the feature store manages those transformations, I'm curious to understand some of the scaling challenges that exist around the definition of a feature and then sort of whether you compute it lazily or eagerly and making sure that you can optimize for the latencies from when somebody requests the value from a feature to when it's able to deliver it, because you're mentioning that, it might be a batch process or it might be a real-time process or it might be trying to merge between both of those where it periodically computes the batch and then maintains a stateful stream computation or aggregation across that to layer on top of the batch data. Some of the complexities that arise as you start to build out this large catalog of features and any sort of usage patterns on the machine learning side too, as far as memoizing the return value so that you don't recompute it every time it gets called, or you might use the feature at one level of the logic flow and then you might need to pull it again with maybe a different parameter or even the same parameter, just making sure that you're not wasting compute time throughout the life cycle of the feature computation as well as the execution of the machine learning model in production.
So what we've done, we support a bunch of engines. Most people that build feature store, they support like Spark, okay? And Spark has its limitations. Some of the ones that you mentioned are essentially limitations of how Spark work and microbatching and all of that. And And also most feature stores, what they do, they essentially build a stream and they build the offline features. And essentially what they do, they copy the offline data set into like a NoSQL data store periodically. So that essentially by definition creates a data skew, because if you haven't copied like for 5 minutes this record of user Joe into the key value store, that means that for 5 minutes this data is inaccurate. Especially important for like time series and time windowed calculations, where if you build a feature in the key value that's average last 1 hour purchases, okay, every 30 minutes, that means that when you go and read that data, it has a 30 minutes skew. And if you keep updating it every 2 minutes, that means you're going to kill the database or kill the computation. Okay. The way that we've addressed it, so first we support all that as well, but we also built some of the logic into the database. Okay, because the database is the thing that gets those updates and it essentially calculates the results instead of responding with the value that's stored in a cell. Essentially has the equation built into the database and it knows how to calculate things like time window aggregations and other things that have those problems of data skewing. Now, also remember where we started. We started by building a database that performs like in-memory database, just runs on Flash. So based on our benchmark, we do like half a millisecond response time. So you can essentially get a feature vector in half a millisecond. We have a deployment in Samsung for like credit recommendation. We enrich 10,000 features on a feature vector. It's data coming, it's recommendation engine for a credit application where they have 70 different sources. Every source contributes, dozens of features to total about 10,000 features for individual user. Now, the deep learning model that needs to go and take a decision, what is their recommendation, every time that it makes an inferencing decision needs to read 10,000 values on every transaction. When they initially worked in the lab, the data scientists finished the work with the Jupyter, et cetera, and said, you know what, let's go and run this thing. They managed to do like 6 requests per second. Okay, that was the number. The requirements for the application in real business workload was about 6,000 requests per second. Okay, they're serving tens of millions of subscribers. So idea is probably not to take 1,000 servers or 1,000 databases and just replicate it. That's really where you have to do so. A mechanism that has much higher concurrency built in. This MLOps challenge of someone built something in Jupyter and now you have to move to something which is more like stream processing. You don't do a SQL query every time, 6,000 times a second. It just won't work. You have to essentially build the results dynamically, doing all sorts of transformations on the data in flight and store it in sort of more of a key value layout. So when you do it, get it in half a millisecond, not in like a second or more. And so this is where we shine. The ability to ingest tons of data and serve them extremely quick. And exactly the same data could be used for training because we have sequential query capabilities. Now, all of that is wrapped in a new framework that we've built, which is not just specific to our database. We took the ideas from familiar with like Apache Beam and Flink and all of that. The key challenges of those frameworks that they're very Java oriented. The data scientists, they like Python by nature, pandas and all of that. So what we've built is an asynchronous engine, which is pretty much like Apache Beam, but it's native Python. It's used async IO and some other acceleration techniques. It also works with the underlying serverless engine. What you do, you write Python business logic. That Python business logic translates into something like Flink, but using this engine we call Story, and it spreads itself across serverless microservices that do the actual enforcement of the transformation pipeline. And by the way, this is all open source and people can play around with it.
It's definitely interesting. I actually spend a lot of my time in Python as well, and actually have another podcast that covers that ecosystem. And as you mentioned, there's a lot of heavy hitters in the streaming ecosystem are coming from the Java landscape. And there is that impedance mismatch between the interfaces that are available for Python developers to be able to execute against them and the ways that those frameworks represent data and process it under the hood. And so that's where a lot of the pain comes from people that I've talked to who are using things like PySpark for trying to build their jobs, because the way that you think about problems in Python is very different than the way they think about it in Spark with Scala and Java.
This really gives the velocity to the data scientist and the data engineer. They write some basic script, and that script runs thousands of requests per second by just like deploying it. We've shown accelerations of 20x on running exactly the same business logic, translating it, compiling it into the serverless processing pipeline, 20x faster. There's some blogs that I've written about it. And also, by moving it to something more Pythonic by nature, you can incorporate all the things that the Python ecosystem developed. So the nice thing about our feature store, it's the only one that doesn't go just to machine learning. We support deep learning. We support NLP. We have a financial customer that actually he feeds the feature store with a PDF document, okay? Extracts the text from the PDF document as another step in this microservice pipeline, runs a sort of a BERT model for text recognition and predictions, extract entities, who are we talking about in that document and all of that. And essentially the final result is stored in a table. So you can build very interesting things if you leverage the ecosystem and you don't try to invent a parallel ecosystem. You just focus on the challenges of making things extremely concurrent and avoid garbage collection, all those things that we do under the hood to make it faster than Java.
Digging a bit more into some of the workflow around feature stores, particularly from the perspective of a data engineer, I'm interested in understanding how the transformation logic is defined and executed, and how the feature store might integrate with something like a Dagster or an Airflow for managing the full flow of the data pipeline from collecting the source information through to building the transformations for the feature store and storing those values in that engine for the machine learning engineers and data scientists to be able to consume them.
So you can use things like Airflow, but the cool thing about what you just described, that it's a federated DAG, federated real-time DAG. So it means that's things like I mentioned, like Flink, but it's not limited to real-time. That's actually the cool thing. You can build batch workflows or real-time workflows. We also work with Kubeflow and Argo, which are sort of the equivalents of another pipeline, which is more Kubernetes native. So we support both the real-time pipeline engine that we developed, but that pipeline can actually also do batch. It's just how you trigger the steps within the graph. And the other one is Kubeflow. The advantage of those engines is that they're more microservice native. So the underlying thing in the graph is a serverless function. If you're familiar with like Amazon step functions, there's another sort of a pipelining mechanism where the individual steps in Amazon step function is like a Lambda function or an Amazon service. So we built something similar, but just again, much higher performance. You can just connect those with streams. The different steps between one step and another, you can actually have like a stream. Another thing that we've done different than those frameworks that you mentioned, part of the problem is that in Airflow is that every step is its own process and potentially its own container or workload. So let's assume I just need a very simple transformation, take a data, drop a column, and then maybe do some other things, multiply by 2, etc. So I will create a very heavy workload, heavy pipeline. For each one of those transformations, I need to essentially go and bring up a process or a container and so on. So one of the things that we've done is that essentially you can co-locate the different steps in the same process or spread them across based on the actual usage. So you avoid serialization, deserialization, moving to JSON and back and all of that. You avoid bringing up containers and down. This is why it's extremely fast in like real-time workloads. But it's also nice for batch workloads. No one said that you have to, waste CPU energy for fun. Just
Digging a bit more too into the sort of breakdown of responsibilities around the producers and consumers into a feature store, how have you typically seen how the workflow orients itself? Where are the data engineers generally the ones who end up defining the transformations for building out the features, or is that something that is usually more self-serve from the data scientist side, and the data engineers are responsible just for setting up the data access and the initial sort of extract and load, or maybe some of the initial transformations for providing the data to the feature store to then do the feature extraction?
I think you're raising a very important point is that in some organizations, there's significant silos. There's like the data science group, the guys with the Jupyter and the CSVs, and there's the data engineer guy, and there's the DevOps guys and the ML engineers now, and like each one works in his own silo. And then when you create those boundaries, from my experience with the customers, the ones that are more advanced, and essentially think of it as, okay, we have a business application to build and we have a multidisciplinary team that collaborates. Those are the ones that I see them like generating projects, getting to production very quick. The ones that are saying, you know what, I'm the data science group and I don't know how to do data engineering, or I don't even know who's the data engineer. Those are the ones where I see the projects are failing all the time, because eventually it has to be a collaboration of the team of data scientists, the DevOps, and the data engineer. Now, it needs to be in a way that the data scientists have to do some analytics, because some things that he's trying out is, let's try and aggregate this feature, let's bring this data, maybe I need to transform it this way, etc. Maybe I need to scale the feature and so on in order to see what's making a bigger impact on the model. On the other end, there are things that like ETL processes, bringing the data from your Oracle or data warehouse and all that. Probably the data scientist is not going to touch that part of the world. So they have to work in collaboration, where sometimes baseline features will be produced by the data engineer, and sometimes data scientists will actually do that work. So this is one critical point about feature stores. They have to be able to speak the two dialects. On one end, data engineers that may want Spark and may want Scala and all of that, or may want to do things that are more heavyweight, and also the data scientists that can just go and consume whatever the data engineer did, or maybe change it and build some new features. Some data engineering tasks, as I mentioned it before, are very data science oriented, like imputing, which is essentially filling up missing values. Sometimes the way that you do the filling up of missing values has a lot of statistics logic built into it. Sometimes it actually runs a machine learning model to predict what are the values that needs to be substituted with. Okay, and those things require a collaboration between the two teams and have essentially having them to work on the same platform. I think this is really one of the things that differentiates us, is the fact that we do speak those two dialects. In our platform, we have a managed Spark, managed Presto, we have Dask, which is sort of in between, the data engineering and the data scientists, and we have like TensorFlow and scikit-learn and all of that. So you have, unlike Hadoop, for example, is a data engineering play that's mostly caters to building data lakes and batch computation. What we're built is sort of the hybrid of the machine learning pipeline, which is like training, model evaluation, serving, model monitoring, drift analysis, all of that, which are very data science oriented features, along with the analytics, stream processing, ETLs, and so on.
And a couple of interesting things I want to dig into out of that. One being the question of data lineage tracking and how that plays into the feature store, where that's one of the big trends that's been coming up a lot lately, is just how do you make sure that you understand the overall data quality questions and where the information is coming from. And that's also an important question to ask from the data science perspective is, I have this feature, it's going to give me this output value, but where is it sourcing the data from? How is it making those computations so that I can understand some of the ramifications that might have in terms of what I'm inferring from the values that it's returning?
Essentially, this is really one of the challenges with the platforms that are decoupled. Like, you have other feature stores. I've interviewed one of them. It's a company that focuses just on feature store. You have a company that's focused just on model serving. You have a company just focused on training, etc. And then how do you connect the dots? Like if the training logic runs and generates a data set, how do you track the lineage across that part? If you have serving that essentially does inferencing and makes a prediction, and that prediction of value, you don't want to know how you got to that predicted value. How do you keep on the sort of the lineage across all those different components? And not to mention data governance, quality policies and all of that. So what we've done, we've worked quite a bit. I had a lot of meetings with Microsoft and Google and other companies, and we tried to create a model of how would an end-to-end solution look like. And we created a work group. And out of that work group, we wrote some documents and modeled the entire problem. The stepchild of that is an open source project that we've created called ML And the general idea was modeling each element in this pipeline. Also the data engineering parts, not just the data science parts. And there's a common thread across all the objects in that sort of metadata database. Everything is versioned, everything has lineage. And because it's sort of more of an end-to-end, like when you're running a job, it auto-detects the process, the git commit of the code in the process, and so on. It essentially tags that job with all that information. So processing elements within the entire pipeline, whether those are data processing elements or model training and so on, they all keep on collecting information about code snapshots, the configuration snapshots. So which scikit-learn version was I running with this experiment, for example? The data lineage tracking, which data went into that process, which data went out of that process. And again, everything is versioned, including the data artifacts that go in and out of each one of those pipelines. So that allows you to create a more holistic solution because what I see, people just go and take, like Tecton and Seldon and Azure and SageMaker and all that, and they stitch their own solution. You find that 80% of the work is just creating the stitching, creating the glue across all those components and, different security paradigms, different way of lineage for each one of those components, different ways of provisioning, different ways of doing upgrades. So by having one framework that we've built for all the operational pipeline, from data gathering to producing model and then monitoring the models, it's much more powerful and it requires less manual work to do each one of the steps.
Another question that I was interested in digging into is once you have the machine learning model built and you've got it deployed, what are some of the types of information that you use to track to understand how well is the model performing? When is it starting to go through model drift? How much drift is acceptable? What are the necessary timelines from being able to say, I've detected a statistically important level of drift in the model to then having the retrained model deployed into production, and just some of the trade-offs that are necessary there, and how much of that responsibility lies on the data engineering and data platform team to be able to manage the production environment for that model, and how much time does the data science or machine learning team spend providing input to or actively monitoring some of those aspects of the machine learning project?
Essentially, there are three different pipelines, if you logically. Okay, we have the research pipeline where we develop the model. We throw some data into a data lake or Parquet files, we run some analytics, we prepare data, we do the training, and then we generate the model. There's a second pipeline, which is essentially we get more of up-to-date operational data, we run stream processing, we do model inferencing, and so on. There's a third pipeline, which we call it the monitoring or governance pipeline, where everything that was generated in the model serving is getting essentially back into yet another stream, sort of an output stream, that records every activity that went up with the model. What was the latency for inferencing? Which data came in? Which data went out? And so on. And that also needs analytics to understand that data. So the drift, what is a drift detection? It's essentially a real-time stream processing on the outputs of the model behavior. And even there, you also have some batch processing because some decision or some insights are not like real time. You have to look into a bigger time window, and maybe you need to incorporate results that came like 2 hours later or 2 days later, and to evaluate those results versus the predicted results. So there's also some batch pipeline. So what we've done, we've combined all of those into a single thing, and the feature store is also an essential part of all of that. In our case, other feature stores don't do it because what is essentially how do you monitor the quality of the model is essentially you have to look into two different things. One is think of it sort of as a data quality or data drift. Okay, so let's assume I was training my model and the statistical behavior of a feature of number of clicks per hour, okay, was that by average you have like 10 clicks per hour per user, or maybe woman this much and man this much, and so on. And based on that, I created a training and I created a model. What is a model? It's just a logarithmic equation. It just takes a bunch of numbers and generates an outcome. Now, If the data right now in production is different, the average number of clicks per hour in production is different, by definition, it means that my model is inaccurate. It cannot make exactly the same prediction if the statistical behavior of the features going into it isn't the same between production and sort of training. So that means that what we need to do, and that's the first mechanism for identifying a drift, is essentially in the feature store, when you adjust features, it essentially auto learns the features. It essentially creates a statistical analysis of all the features that go into the feature store and stores the statistical analysis of those features. In addition, in real time, it calculates the real time statistical analysis of those features using stream processing by tapping on the model serving containers. And then what you essentially do, you is compare them in real time. You compare the offline feature statistical analysis that was created before training with the real-time statistical analysis. And this is how you can create a drift indication for the data. And again, the way that we did it is integrated in the feature store. And that also goes back into my point that let's assume that you don't have your own model serving engine. You just come with a feature store as a vendor. So how would you integrate all this functionality that I just said into a bunch of different things? You have model serving companies and you have training company, model training companies, you have feature store companies and so on. So they all need to agree on the same metadata. So the feature store will store the statistical analysis in a certain patterns that the training will generate it, and the server will know how to generate a similar pattern just in real time. And then there will be another fourth product of drift analysis that will need to know how to work against all those four schemas. That's extremely hard if you don't build an integrated approach like we did. So in our case, it's actually the nice thing, it's glueless, because the minute that you find the feature, you already defined the fact that the system needs to start gathering the statistical analysis. And it's using the exactly same stream processing technology I mentioned before that does in order to calculate the gaps and time windows and all of that. And that's for the data drift. There's also accuracy drift, which is slightly different, which it means essentially we have to compare the results, not the incoming data, the results beyond the statistical pattern of the result, which is also important, with the actual data. So let's assume I predicted the stock market is going to go up and it went down. So after a few minutes, I know if my decision was correct or not. So I can essentially go and just do some time shift on the result and compare the training data with the shifted actual data, and I can also measure the exact accuracy of my model. So that's another way of monitoring.
Modern data teams are dealing with a lot of complexity in their data pipelines and analytical code. Monitoring data quality, tracing incidents, and testing changes can be daunting and often takes hours or days. Datafold helps data teams gain visibility and confidence in the quality of their analytical data through data profiling, column-level lineage, and intelligent anomaly detection. Datafold also helps automate regression testing of ETL code with its data diff feature that instantly shows how a change in ETL or BI code affects the produced data, both on a statistical level and down to individual rows and values. Datafold integrates with all major data warehouses, as well as frameworks such as Airflow and dbt, and seamlessly plugs into CI workflows. Go to dataengineeringpodcast.com/Datafold today to start a 30-day trial of Datafold. Once you sign up and create an alert in Datafold for your company data, they'll send you a cool water flask. Another aspect of the statistical analysis of the models and understanding how they're supposed to be behaving is the question of testing and validation and propagating the model from the experimentation through to the training and validation stages and then into production, and just how you manage the overall continuous integration, testing, and continuous deployment process for machine learning projects.
We're very oriented towards CI/CD pipelines, like in microservices, and we use either the traditional tools that in the Kubernetes ecosystem, like Kubeflow or others. Also, within all the frameworks that we've done, there is a way to do like Git hooks and things like that. So you can essentially, we have a nice demo where you can just push a commit, a change in a data definition or a training Python code or whatever. And as you push this commit to a Git, it will essentially triggers a CI workflow That's a CI workflow runs the machine learning pipeline and responds with the actual accuracy of the model based on all the training pipeline. It throws it back as a pull request comment on GitHub. So essentially, someone can actually see, just like traditional CI, it tells you, okay, this is the accuracy of the new model that was trained. And then you could take a decision by just making a comment on your pull request saying, you know what, go deploy it into a test cluster or this specific model into a test cluster and so on. And you can also create review process because in Git, you can say, you know what, the only guy that can do approve a pull request is this guy. I know that there are some platforms that have their own like built-in capabilities for that. We prefer something more standard, more open approach, and we believe that is the right mechanism to, whether it's GitHub or GitLab or other Gits, we believe that's the right approach to build your automation around.
We've spent a lot of time talking about a lot of the problems that Iguazio solves and at a high level discussed some of the architecture, but can you dig a bit deeper into how the overall Iguazio platform is architected and some of the integration points and extension points that are available for bringing Iguazio into a company's existing data platform?
Our key focus is we don't have to do everything in the pipeline. Our key focus is the key challenge that most people are facing is operationalizing machine learning. You hear those things like 80% of machine learning projects fail because how difficult it is to make them operational. And we started the show. We talked about it. The guy with the Jupyter that plays around with the CSV, and then he needs to make it something that actually works in a real pipeline. They don't have any clue. More knowledgeable organizations understand that they need to now bring Kafka in and bring stream processing and automation and Spark and so on. But many organizations have some junior data scientists that just finished school. They don't have any clue on how to build it. So this is the area where we're focused on is how to accelerate this process of, okay, you played around with your Jupyter. Now let's see how we scale this. Now you can choose to work with AutoML tools like Data Robot. We also have strong partnership with Microsoft Azure, with SageMaker, and so on. You could choose to do the training using AutoML, but the biggest challenge is creating those operational pipelines. And 80% of the challenge we just spoke about is about data. Data engineering, real-time analysis, monitoring of data, statistical analysis of data, and so on. Those are the things that most data scientists and data science group, they only tackle them when someone starts shouting, why don't we do anything productive for the company with all this data science group that we just created? This is why we also appeal to data science because we help them translate the built in the lab with minimal efforts into something that actually yields value to the business, recommendation engine or predictive maintenance logic. And so the way that we work first, much of our technology is open source. It's standardized around the standard component like Kubernetes is the cluster framework that we work on top of. We work with all data sources. And we also have our own real-time database that is very essential for the process, but you don't have to use it. It's not the data lake. It's like this thing that allows very quick shuffling and transformations of data. And we have all those serverless engines on top and an automation layer in order to streamline the process and eliminate 80% of the work or even more. We have customers told me, last year we generate a single pipeline to production. We use you guys for like 6 months. We already produced 4 projects and productize them because that gives them the velocity, all this automation that we built. And by the way, people don't have to buy our product. We are happy to work with some of our open source technologies and people that like to adopt them. We know that tier 1 cloud providers are using some of our technologies. We're good with that as well.
With all of the experience that you've built up working in the machine learning space and helping to provide the tooling and automation for companies to be able to bring their ideas into production, what are some of the gaps that you see still remaining in the overall tooling or processes, whether in terms of the development workflows or organizational aspects that are still open questions and still need to be addressed for managing the overall lifecycle of machine learning projects?
I don't think that there are major things that are missing. I think, now feature store are becoming more and more mainstream. Many people still don't understand maybe the difference between like a feature store and a data catalog. I think we try to make it clear here that feature story is also about the automated transformation and the ability to do real time and offline, and relieves a lot of the operational aspects. It's not like a catalog you just register offline data lake data in. So I think feature story is going to solve a lot of the challenges. On the machine learning side, I think AutoML actually makes it simple even to data engineers to go into data science if you think about it, because a lot of the black magic was, okay, do I use XGBoost or do I use like a logarithmic regression or whatever, and the right parameters to use and so on. And with all those AutoML tools and products and open source projects, now it's sort of becoming commodity. So the real number one challenge that people have, and I keep on hearing that 80% of it is about how do we select the features, the best features, how do we produce the best features, and then on the other side, how do we track the behavior of the model, do retraining, and do all those operational challenges. I don't think there's significant missing tools. Maybe slightly on the deep learning side, there's still more. It's still complicated to build neural networks and all of that, and still a lot of voodoos over there. But I think the biggest challenge is having a more integrated approach. How do you choose the right tools out of this jungle? There's probably thousands of products and open source projects that do machine learning. How do you create an ecosystem out of all of that that talks to each other and fill all those? That's a lot of things that we're trying to do, whether it's using our open source project or integrating our open source projects with the best of breed tools in the ecosystem or the best of breed managed cloud services in the ecosystem. So trying to reduce as much as possible the friction of building a solution. I think that's the key challenge. How do you reduce the friction of building an operational pipeline? And some of it has to do with politics. Because again, I told you before, I see the successful companies we work with are the ones that broke the barriers. There's no silos. It's like a team, and the data scientist can talk to the data engineer across the hall and ask him for a favor. And then when he finishes, he talks to the DevOps guys and they bring up the container. And one of the challenges, for example, is throwing stuff over the wall. If the data scientist writes some code in Jupyter, and then someone needs to go and transform it to like Docker container that runs on Kubernetes, essentially someone just takes the code, probably throws away 90% of it and recodes it. But if they work in collaboration, for example, some of the mechanisms we offer, others offer, that essentially data scientists write some code, you maybe put some hooks for exception handling, the data engineering, the DevOps guys improve that. Now, let's assume we need to tweak something in the code. Instead of redoing the entire ceremony, the data science can go into the code that's already ready for production and change a parameter or add a parameter. It's not necessarily redoing the entire ritual. We have to be very conscious of people's time and creating more of a continuous deployment and integration workflow in collaboration of those three personas.
And in terms of the ways that you've seen the Iguazio platform being used and some of the different open source projects that you've built, what are some of the most interesting or innovative or unexpected projects that you've seen built with your technology?
So actually one cool project that we've engaged with throughout the COVID time was one of the hospitals in the Middle East essentially used us for real-time patient deterioration analysis. So essentially, think like on every patient, you have lots of different data sets. You have the medical record, he has certain diseases, male, female, age, and so on. Then you have all sorts of measurements, like yesterday you took blood sample and that was the result, or you took some, urine test or whatever. Those things are being done periodically on now sort of frequent basis, just like yesterday you did this and a week ago you did the other thing. And there's also like 7 different data sets. One of the other real-time data set is the bed sensor logic. So the real-time heart rates, movement sensors, and there's lots of sensor in a patient's location. So analyze all those different things, the medical records, the measurements of his samples, the real-time data coming from the bed, potentially also things like X-rays that you've taken that require deep learning, and you incorporate it into a real-time decision. Okay, this patient must get this treatment in a pretty urgent, and actually throw an alert to the doctor that he has to go and treat the patient. as well as show it in a nice dashboard with like reds and greens and showing which patient need to get which treatment in what importance. So think like prediction of the deterioration of patients. So that's one pretty interesting application, also important one.
Yeah, it's definitely very cool. It's always great when you're able to see the tools that you build able to be used to help people. In terms of your experience building the Iguazio platform and the open source technologies that you use and produce and helping to scale the business around it, what are some of the most interesting or unexpected or challenging lessons that you've learned in that process?
I think one of the challenges that we keep on facing, one of the key values that we bring is automation. Automation in order to save time for people, go faster to production. Where we sometimes see challenges is internal teams, especially when you go on-prem, because in the cloud, people are very much oriented toward let's go and grab some pre-baked service and use it. But especially with IT, which is essentially sort of an oxymoron, because usually the more modern, the sharper ones are the ones working on the cloud, on all the latest and greatest. Sometimes in on-premises, you don't have like the best technologies and working on internal ITs and all of that. But for some reason, a lot of organizations want to invent things by themselves. And they'll say, no, we can build it in a week. Now, they can't build it in a week. We have like 80 people and we're working on it for a few years. It's not something you can build in a week. Or sometimes you have consultants that come and say, you know what, we're going to build some stack and we're going to build some TensorFlow for you and we'll build everything. And then you ask, okay, but like TensorFlow every few weeks changes and you'll need to modify your containers. And once the consultant goes away, how are you going to keep on maintaining that work? So you rather have a product versus do things yourself or with some third-party consultants. It reminds me of also speaking to a CIO of one of the insurance companies that we work with, bitching about consultants in general. So they're saying, those consultants, they interview us, they ask us what's the data, how is the data used, and all those questions about the data. We sort of waste tons of energy. I'll explain to them how it works and all that, what kind of aggregations we need to do, what's the business logic and all of that. And then they go run some scikit-learn on all the things that we've done. I'd rather just get a data scientist and instead of teaching the consultants and then paying them and then they leave and we sort of stuck with something we don't even know how to maintain, I'd rather just bring a couple of data scientists and have some automation built for them so they can produce the business logic by themselves. Because the biggest thing you need is to understand the business logic of your business. If you don't understand the business logic of your business, you can't really build a solution because you always have analysts that you have a gut feeling about, what are the trends that you need to monitor and things like that. Those are things that if you bring in a consultant, that means that you have to go and teach the consultants all this business knowledge that you've gathered throughout the years. Yeah, so this is really what our role. We also have data scientists in the company, but their role is essentially they're data scientists that are very oriented towards operations. They also have data engineering skills, they have DevOps skills usually, and their role is to work with the customer data scientists and empower them and teach them how to move away from sort of a Jupyter concept and to move to Python and do some unit tests and build things in a more reproducible way and things like that, and add experiment tracking and add other things potentially needed to make it something that you can just like throw it into a machine, it will retrain itself, it will run at scale and all of that. So what we're trying to do is take organizations and teach them how to, walk and run instead of doing it for them, giving them the fishing net, instead of the fish.
For people who are looking to be able to build these machine learning pipelines, they want to be able to get their models into production. What are the cases where Iguazio is the wrong choice?
So if it's like entirely batch-oriented flow and also small-scale data, if Jupyter is good for you or you don't have an operational pipeline, there are a lot of companies that, they use the machine learning model and they do some batch prediction and they create some fancy report for the CEO, show that we could have done something different. So those are probably not a good choice for us. What we're focusing is on people that build applications around machine learning, more operational, more online, things like recommendation engines, fraud analysis. I gave the example of the hospital, the patient monitoring. We do predictive infrastructure monitoring with a huge scale, running essentially all the network appliance, all NetApp predictive maintenance run on our platform on few virtual machines. So, we have airports. We actually monitor everything like belt, condition, cameras, all that, real-time insights, and say which plane goes first into the gate, things like that. So operational use cases where you're actually trying to put machine learning and AI to work for you, these are the ones that excel. If you have a data set, you want to run some training and make a report, don't use us, okay? Or if you have very small scale or you're not trying to create sort of a CI/CD kind of mentality in the organization, don't use us. When I see that the organization is very, very siloed, like the data science group, I ask them, okay, how do you do the real-time features? They say, no, it's not a problem. I say, how come it's not a problem? You have to do it. And I said, no, we throw everything we do, we send it over to the other department, and they're essentially recoding everything. So there's no problem. It's someone else's problem. So we can't fix it because if politically the organization doesn't know how to work together, we'll go and run into the wall.
And as you continue to build out the technical and business capabilities of Iguazio and continue to contribute to these open source frameworks that you support, what are some of the things that you have planned for the near to medium term? And what are you most excited about in the overall machine learning space?
I love technologies. I'm excited about many things, but I think what key focus areas for us right now are enhancing the feature store, making it more powerful, more automated, it's more scalable, higher performance, and so on. That's one thing. The other thing is that we've produced this sort of DAG technologies. You can build a real-time and offline pipelines or serverless pipelines, and they have a lot of built-in primitives that we created essentially a library of things like aggregators, joiners, things like that. Think of it like Lego building blocks, like a playground for building analytics using higher level Lego bricks. And then it just compiles to something extremely fast and that can work on batch or real time. So that's something that we're going to expand the different primitives on and expand the other capabilities to the harder problems of data consistency, exactly one semantics, and so on. And the third tool is also leveraging the other two technologies. They're all sort of connected, is all the sort of post-production aspects of enhancing the model monitoring capabilities, alerting, retraining, data governance, and that side. So you see a lot of our focus is not necessarily making better AutoML. I think that market is like already very saturated and are good open source projects in that field. And also that's something that we support in our pipeline. You can just launch a training job in our Azure ML or SageMaker from within our pipeline. So it's not there that we think we need to waste energy on. But the other things that I mentioned, like the feature store, the real-time pipelines, and the model monitoring, analysis, retraining, serve the CI/CD for MLOps, the areas where I think there's the biggest challenges today in the industry around our theme, which is operationalizing machine. Would you agree with that?
Yeah, I definitely agree that the biggest challenges that I've seen in terms of understanding and adopting machine learning is just figuring out how to get access to the data, how to operationalize that, and then just managing the overall life cycle, where a lot of the work that I've seen going into machine learning is in more of these static use cases that you mentioned, where you're just pulling the data, you're building a report, and then you have something fancy to show for it, but not as much of the sort of building it into the core of your application. And that's where a lot of the current energy I see going into the overall space is figuring out how do we make this maintainable, particularly for smaller teams who don't have the capacity of a Google or a Facebook to, just throw a bunch of engineers at the problem and work their way through it.
Yeah, and we also invest a lot in usability. We have a couple of UX designers working for us. So because the problem, we have lots of capabilities and lots of technology. When you have lots of technology, it's not so trivial for the novice. There's a term called clickers and coders, if you're familiar with that. There are platforms like RapidMiner or whatever, where you just like click, 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 or even H2O or Data Robot. You throw in a CSV and it generates a model for you. But it's very limited because it only works with the CSV. It probably won't work with a terabyte worth of data. And also, it's very canned logic. It has a bunch of very specific algorithms that it works. So we provide huge flexibility. So it's not as like you push one button. There are a few buttons to push. So we're trying to make also the experience Much easier, incorporate wizards, do even some AI ML in the way that we present things to make it simpler and slicker to consume.
For anybody who does want to get in touch with you and follow along with the work that you're doing, I'll have you add your preferred contact information to the show notes. And as a final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
One very interesting point, I was speaking to some Gartner analysts and saying, okay, you know what, like machine learning used to be manual and now there's like auto ML, okay? DevOps used to be manual and now there's serverless or all of that. Like in data engineering, we're still serving the Stone Age, okay? SQL queries and all of that. So, I think that feature store is not just for machine learning. If you think about the same concept that you've built machine learning for because you want to simplify it for the data scientist, you can actually apply the same concepts of a feature store to also data engineering, to reports. But one of the things that we've done is pretty unique in our feature store. Most feature stores output is key value table or data warehouse or Parquet or BigQuery or something like that. We can output from our feature store also time series SQL data. So if you want to put a BI dashboard on top of some features that you've built, it's actually we support real-time dashboards like Grafana, and we support also BI dashboards through JDBC plugins. So you can think about like feature stories like the next level of abstraction also for the analytics guys, for the traditional ETL flow. But that's more slightly futuristic for some of the data engineers, I think, but that's my gut feeling. What do you think about it?
I definitely think that using the feature store as a step in the overall pipelining of a data engineering flow would definitely be interesting. And it could definitely help to simplify some of the discovery that goes into it, particularly as you grow the number of pipelines where there are going to be commonalities in terms of the transformation steps that you build or some of the aggregations that you need to run across different data sources, and using the feature store as an output for some of those downstream stages, I think could definitely simplify a lot of the complexity that goes into building and maintaining all of these pipelines.
It doesn't have to feed a training model. It could feed an event-driven logic, simple event processing. It could feed a dashboard or something like that. And not everything is just a bash like querying, SQL and all of that. You can update a SQL database so you can build a BI system on top of it, but keep it fresh. Still, there's lots of challenges on stream processing, all the challenges around always on and auto scaling and exactly one semantics and all of that. So this is another area where the traditional, Kafka, Spark streaming and all that, you can displace it with something which is more like intelligent and more abstract, and they build it based on those sort of Lego building blocks I mentioned. Like, think one of the nice things we have in the higher level abstraction is dealing with aggregations. I like to show this sort of hospital example. We have some of the code in the open. Like I'm building aggregates for all the telemetry data of a patient in 3 lines in Python. Now, if I need to build it in SQL, that's few hundreds lines of SQL that's undebuggable. So this is another thing that we can start thinking about. Okay, how do we build a higher level abstraction logic, data engineering at?
Yeah, definitely something that I'll be interested to dig a bit more into and hopefully see some different frameworks start to, or best practices guides factor into the overall approach to data engineering and data management.
One of the interesting phenomena that could happen is sort of a mix between data, between predictive and prescriptive. Okay, so think of how do we create a feature? We run some analytics, okay, and we create a new feature. But some features may be predictive. Like I can add a column, like imputing, I give it as an example, or maybe one of the columns essentially needs to be sort of a predictive value using a model. So today we have like, okay, those guys do data engineering and then produce a set of features, and those guys do machine learning. They take the features and build some predictions. But what if all that gets mixed? The data engineering pipeline includes machine learning logic. Like, I gave some examples, like in NLP, converting unstructured data to structured data, like creating predictive value. So I think one of the things that we may see in the future is essentially that things start to get mixing. You'll see machine learning in the analytics and analytics in the machine learning.
Yeah, I've definitely already started to see some of the machine learning applications get factored into some of the data engineering pipelines, particularly in the data quality ecosystem, where a lot of companies are starting to build models around doing statistical analysis of column values to understand, is the outlier something that is genuinely bad data, or is it something that is actually expected based on some other external factors to the business that, might contribute to larger than normal seasonal drop in business because of COVID, for instance.
Yep, exactly.
Well, thank you very much for taking all the time today to join me and share all the work that you're doing at Iguazio and working to help bring machine learning into production. It's definitely an interesting and challenging problem domain. So it's always great to speak to people who are helping to simplify that and make it more accessible. So I appreciate all of the time and effort that you've put into that. And I hope you have a good rest of your day.
Thank you very much. And it was fun talking to you.
Likewise. Listening. Don't forget to check out our other show, podcast.init, at pythonpodcast.com to learn about the Python language, its community, and the innovative ways it is being used. And visit the site at dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. If you've learned something or tried out a project from the show, then tell us about it. Email hosts at dataengineeringpodcast.com with your story. And to help other people find the show, please leave a review on iTunes and tell your friends and coworkers.